Hello everyone, this is the start of the video lectures for Module 2. Most of Module 2 is going to be done through these video lectures, and we will have some in-class time together as well for Module 2. So to get started on Module 2, we're going to be talking about pressure distribution in a fluid, and this is equivalent to Chapter 2 in your textbook. So to follow along, you would follow Chapter 2 in your textbook. And the first thing we're going to say is that when fluid velocity is zero, so looking at a fluid with zero velocity, we call this a hydrostatic condition. Okay, so it's called a hydrostatic condition, which essentially means that the fluid velocity is zero. And when the fluid velocity is zero, we can say that the pressure variation inside the fluid is due to the weight of the fluid. So the pressure variation in fluid is due to the weight of the fluid. So if the fluid were to be moving, there could be other pressures that are acting upon it. But if a fluid is completely at rest, then we can say that the pressure variation in the fluid is only due to the weight of itself. And let's look at sort of an illustration of this in terms of a little diagram. So let's look at the pressure force and try and understand what the pressure force is on a fluid element. And to do this, what I'm going to do is I'm going to copy over a figure from your text, which is also available in your Module 2 handout. So you have this figure in your handout. And what we see here is that we have an element of size dz, dy, dx, and we're going to study what the pressure does on this specific element. So the first thing we can say is that pressure is a function of x, y, z, and time. And we can also say that pressure usually causes a net force on an element. So what we mean by that is that if we look at our diagram here, we see that we have two sides to this diagram. We have this left side with a certain pressure, okay, and this pressure is P, is a pressure P. And then on the other side of our fluid, we have this other pressure which says it's P plus dP dx times dx. Okay, and we're going to look into that, what that actually means. So if we were to sum the forces on the left side, we could say that the force on the left side would be equal to pressure times dy times dz. Okay, and I'm going to use a capital P for pressure. The book uses a lower p. I'm going to use a capital P all the time. Okay, now why is the force equal to P dy dz? So if we remember, force is equal to pressure times area. The area of this element here is dy multiplied by dz. So essentially, this term here is equal to the area. Okay, now looking somewhere else around the element on the other side of the element, we are now faced with a slightly different pressure because we remember that pressure is a function of x, y, z, and t. So the pressure on the other side could be equivalent to P, but it could be something else. Okay, so we can say from the right side that the force is now equal to pressure plus a differential of pressure with respect to x, so how much the pressure changes with x, multiplied by dx, which would be your distance. Okay, so this is the distance. And the reason we have this distance is because P is dependent on X. Okay, so if we have, so let me finish the equation. So then we multiply by the area that it's affected on, which would be dy dz. Now, this dp dx, why do we have a dp dx? Why isn't it just pressure? Because we're going to assume that our element could have a different pressure on the left and on the right. Okay, so because pressure is dependent on X. Okay, we're going to say pressure is dependent on X. And the pressure can vary depending on the X position pretty much. Okay, now obviously this dp dx could be equal to 0. So this dp dx could be 0 if in equilibrium. So if we have this element is in equilibrium of pressure, we can say that dp dx could be 0, and then it would be perfectly in equilibrium because we would have our element like this. Okay, let me draw it in the same way. We would have our element with our pressure coming in and our pressure on the other side, and the pressures would just both be pressure. And then our forces would be pressure times dy dz. And same thing on the left side. Now, this would mean that it is in equilibrium. Now, what we're trying to illustrate here is if it is not in equilibrium and if the pressure is acting on the two x faces and the pressure can vary arbitrarily, we need to come up with an equation for the change in pressure between the left side and the right side. And the equation for that change in pressure is dependent on the distance x, and then we multiply by the distance x to get rid of the distance. Okay, so this is how we would illustrate that arbitrary change in pressure on the left and right side. So let's do a sum of the forces in the x direction. So now let's take our element and let's look at a sum of the forces. Let's do a net force equation in the x direction. And this is why we do this illustration. We're trying to derive something out of this. So the net force in the x direction, because we're using a differential element, okay, the element is dy, dx, dz, we're going to have a differential force. So we can say dfx is equal to, and we're going to assume that positive is towards the right. So positive is towards the right. Okay. We're going to say that dfx is equal to p dy dz, which is going towards the right, and then minus whatever's on the left side. So p plus dp dx times dx multiplied by dy dz. And if we look at this equation more closely, we see that two things cancel. We see that our p dy dz minus p dy dz cancel. So the two p's are actually going to cancel. Okay, they're canceling out. The two p's are canceling each other out. So we get that dfx is equal to minus dp dx multiplied by dx dy dz. Okay, we're left with only one term. And in the same way, we could do the same exact analysis looking at the other elements. So we could do the same analysis looking at the top and the bottom, or looking at into the box and out of the box here. So looking at the three different sides. And if we look at the three different sides, we could actually get our forces in the other direction. So the forces in the other direction, if the pressure varies arbitrarily, we would get dFy is equal to minus dP dy multiplied by dx dy dz, and then we would get dfz is equal to minus dP dz times dx dy dz. Okay, so we can do the same thing in all the directions. Okay, and what we can actually, once we have all three worked out, we can actually figure out what our equation for the whole force due to pressure is going to be equal to. So the force on the element due to pressure, so I'm going to call it dF press, is going to be equal to, in the minus I direction, and we'll talk about that in a second, differential P with differential X, minus J times differential P differential Y, minus K differential P differential Z, multiplied by dx dy dz. Now, what can we recognize out of this? So there's two things we can recognize out of this. One thing is that this term right here is the volume. So this term is the volume of our box, our differential box. So that's our volume. And we can also say that this term right here, and this you might not know, but this is going to be a new thing. This term right here is what we call the gradient operator of pressure. So it's essentially the gradient operator of pressure. So what the gradient operator of pressure means is that it allows us to figure out what the gradient in pressure is. Okay, so if we have an element shown as above and everything is in equilibrium, all the pressures would cancel out. Okay, we would just have pressure on all sides and all the pressures would cancel out, and the force due to pressure would be equal to zero. The net force vector would be equal to zero. Now in this case, the net force, like if we have random pressure applied in the X, Y, and Z direction, the difference in pressure and the net pressure force vector would be not zero. Okay, so that's the equation for when it's non-zero. Okay, so we do realize that the absolute pressure doesn't matter. It's the difference in pressure and the pressure variation that matters. And that's found in the gradient. And the gradient operator can be written as an upside down triangle. Okay, so that means that dF press is equal to minus delta P multiplied by dx dy dz. Now dx dy dz is the unit volume. It's the volume of our differential. So a differential square a box is a very, very small box. So we can rearrange this equation and bring the volume to the left side. And we can say that dF press divided by unit volume is equal to minus delta P minus, sorry, not delta P, but the gradient of P. Okay, this is the gradient operator. And we can rewrite the pressure of F, the force of pressure divided by unit volume. We can rewrite this as little f press. So little f is just the force per unit volume. Okay, so this is just force per unit volume. Just a different term with a lowercase, essentially. Okay, so what we can conclude from this is that the pressure gradient, if there is a pressure gradient, it will result in a net force. So the pressure gradient, which is also thought of the pressure difference between 2 points, causes a net force. And this makes sense in everyday life, right? In everyday life, if we have a high pressure somewhere and a low pressure somewhere else, what happens is the pressure sort of equalizes. The high pressure region goes towards the low pressure region. It creates a force from the high pressure to the low pressure. And this is what governs flow. This is what explains how flow works and explains how pretty much the whole of fluid mechanics works. Now, in addition to the force due to pressure, is there another force on this element? So let me copy this element over again so that we have it again. Is there another force that acts upon this element? Can anybody think of another force that applies to this element? The other force that applies to this element is gravity. So the gravity works on the element as well. Okay, I'll just write element 2. And in the same way as our pressure force, how is our gravity going to affect this element? Well, we can write that the force due to gravity would be equal to the density times gravity times the acceleration due to gravity, okay, little g, multiplied by dx dy dz, okay? And little force gravity, which would be divided by unit volume, would just be equal to rho times g. Okay, so that's the next force that is applied onto our system as well. Okay, if we go further than this, If we go even further than this, we can say that in addition to gravity, we could have another force. If the fluid is in motion, so if the fluid is in motion, we will have surface forces due to viscous stresses. So you can see how we're complicating the problem by adding gravity and now adding acceleration. So density times acceleration would be equal to the sum of the forces, which would be equal to our force per unit volume of pressure plus force for gravity plus the force from viscous stresses. Okay, we call this a viscous force. And so we can conclude, and we'll look at the viscous force later on. We don't necessarily have to look into it right now. But essentially, what we have now is we have an equation that can be simplified to this. We have the gradient of pressure. So the density times the acceleration is equal to the gradient of pressure, okay, plus rho g. So the sum of the forces plus rho g plus F viscous, okay? And this is acceleration here. The reason I put density times acceleration is because we know that force is equal to ma, okay? And little force, since it is divided by the volume, would be equal to rho a. Okay, that's why we can use this equation here. Now, what it means is that the acceleration of our element, if it is in movement, is going to be caused by the force due to pressure plus the force due to gravity plus the force due to the viscous forces. Okay, that's really important. Now, in hydrostatics, when we're looking at static fluids called hydrostatics, viscous stresses are zero. We have no viscous stresses, so we have no stresses caused by viscosity. And remember, viscous stresses are caused by inducing movement into our system. And that means that acceleration is zero. Our system does not move if there are no viscous stresses. So the acceleration is zero. So in hydrostatics, we can say that the gradient of pressure is only affected by gravity. So plus rho g is equal to zero. So we have a direct relation between the gradient of pressure and gravity. That means that the gravity is going to affect the pressure with depth pretty much, because gravity only occurs in one direction. But we'll look at that in a little bit through example problems as well. Okay, so let's move on from here, and we've created this equation for hydrostatics. Okay, this is valid for hydrostatics, that the gradient in pressure is related directly to only gravity. So only gravity, if the fluid is at rest, is going to affect the pressure. And we'll look at how it will affect it in a little bit. So let's look at some other things that are also looked at in thermodynamics in terms of understanding what is happening. Let's have a discussion about what gauge pressure means and what vacuum pressure means. Okay, so gauge slash vacuum, or vacuum slash gauge pressure. And what vacuum or gauge pressure means are the following. So let's say we have an atmospheric pressure equal to 100,000 pascals. Okay, that's usually close to our atmospheric pressure. And this can be rewritten as 100 kilopascals as well. Okay, now let's assume that we actually have in our system today, or in the air today, we have an absolute pressure. So the total pressure is equal to 120,000 pascals, or 120 kilopascals. Now, how do we measure this absolute pressure? How do we actually measure the pressure in the atmosphere related to our typical atmospheric pressure? Well, what we do is we measure the difference between a pressure perceived versus the atmospheric pressure. So if you fill up your tires at the gas station will tell you that your tires are at 33 psi, or it'll tell you that they're at 2 2 point 210 kilopascals. Okay, your tires will be at 210 kilopascals. What that means is that your tire is actually at 210 kilopascals over atmospheric pressure. It's measuring relative to atmospheric pressure. And that's why it's called gauge pressure. So gauge pressure measures the pressure difference between your absolute pressure, which you're reading, minus your atmospheric pressure. So P gauge can be said to be equal to P absolute, which is an absolute reading, which we can't make, minus P atmospheric. So essentially, when you're reading your tire pressure, you're reading your pressure gauge. And your absolute pressure would actually be your atmospheric pressure plus your gauge pressure. So absolute is equal to P gauge, which is the one you usually measure in real life, plus P atmospheric. So you're measuring the differential between absolute and atmospheric, essentially. And conversely, if P is less than P atmospheric, we use a different term, but it's exactly the same thing. We call it, let's say the absolute pressure is equal to 80 kilopascals. Then now we have a pressure that's less than atmospheric. What we call this type of pressure is P vacuum. Okay, so this is called the pressure of a vacuum. And it's just P atmospheric minus P absolute. So you're measuring now a vacuum, which is less than atmospheric, but the pressure absolute is always, there's still a pressure. Pressure cannot be negative. Absolute pressure, so absolute pressure cannot be negative. So there's no such thing as negative pressure. And I like to use a little diagram to illustrate how pressure readings work essentially. So if we have, and I use the same in thermodynamics as well. So if we have pressure versus the absolute zero, okay, so this would be the absolute zero pressure, and atmospheric pressure is somewhere here, so that would be like equal to 100 kilopascals. If we have a pressure higher than atmospheric, it would show up in a line up here. So it would show up right there. And this would be 120, for example. And then we have another line and I'll extend this line a little bit more just so we have some space, is going to be equal to 80. Now, what is the absolute pressure? What is the gauge pressure? What is the atmospheric pressure in this case? So the absolute pressure is always the pressure starting from 0. So this is the P absolute. Okay, that's the absolute pressure. Then this is obviously our atmospheric pressure, P atmospheric. And the difference between atmospheric and absolute is our P gauge. And our P gauge is usually what we measure in the real world, because we have atmospheric pressure everywhere. Atmospheric pressure is all around our body, but we don't feel it because it equals out. Everything is 0, right? If you're just standing there, you don't feel 100 kilopascals of force going to the left and 100 kilopascals of force going to the right. Now, if you start running, you start feeling some wind. So you do start feeling some pressure. How do you measure that pressure? You measure that pressure relative to atmospheric. So since you have atmospheric pressure always there with you, you're going to measure it relative to the atmosphere. And that's what we call pressure gauge. In the same way, if the pressure is lower than atmospheric, which can happen, in some cases, you're going to have the opposite of pressure. You're going to have a vacuum effect. If we take out some air from a room, we might have less than atmosphere. And in this case, so with the 80 line, in the case of the 80 line, this would now be our pressure absolute. So you can see that our pressure is still positive and still starts from 0. And now our pressure of vacuum is going to be the pressure difference from atmosphere to vacuum. Okay. Now, in our problems, if you are not given any extra information or you're not given any type of pressure gauge reading or anything like that, you can assume absolute pressure. So if they give you a pressure in a problem, you assume absolute pressure, except if it tells you that it's gauge pressure. Okay, so in our problems, you'll be able to assume absolute pressure. Okay, so moving forward from this, that should sort of explain how pressure is read. Okay, that was the goal of this previous part. And if you do want to read more about it, just search like difference between pressure gauge and pressure atmospheric and pressure absolute, and it should work out. Now, let's get back to, so this was just in a part to explain what pressure was, just to make sure that we know how we read pressure. And in our equations, we're mostly going to use absolute pressure, okay? All the theoretical equations use absolute pressure, okay? That's really important. So now, let's go back to where we were before. So we had said that if acceleration is 0, we know that the force viscous is equal to 0. And essentially nothing is moving, so we have minus, sorry about that, so minus the gradient of P plus rho G is equal to 0. Density times G is equal to 0. And we can rearrange this equation by bringing the gradient to the other side, and we finally get that the gradient of P, so the difference in pressure, is equal to rho G. So it's only affected by gravity. And this is for a fluid element at rest. Okay, that's really important. Okay, so it's in a fluid element at rest. And we're going to assume that we're also going to assume from our diagram earlier that the plus z direction is up for our coordinate system. So if I go back to the earlier diagram, just by scrolling up, I see that z is sort of out of the page, okay? and Z is going to be considered up. Okay, so this is considered up. So X and Y are sort of planar, and Z is up. So we're going to assume that our coordinate system is going to be like this. We're going to have Z up, and then X like this, and Y sort of out of the page, essentially. Okay, that's going to be our coordinate system. So we can say that gravity, if we look at gravity in itself and we look at the direction of gravity, gravity is occurring in which direction? Can you tell me which direction gravity is occurring in? Gravity is acting down. So it's not acting up, right? It's acting down. So it's going to be acting in the negative Z direction. So gravity, our gravity, um, our gravity vector is going to be in the minus G direction with respect to K hat. Okay, and that's just IJK. The way we write IJK is we have the way we write IJK is that we have IJK and K is equivalent to Z. So we can say that gravity is acting down. The reason why we write this is because gravity is acting down. So now, we now know that looking at our gradient operator, we have three terms to that gradient operator. We have dpdx, we have dpdy, and dpdz. Now, what are dpdx and dpdy going to be equal to? Try to think about it. If there's no acceleration, then there's no difference. There's no acceleration other than with gravity. Gravity is only affecting in the k or the z direction. So this is going to be equal to 0, and this is going to be equal to 0. So these two are going to be equal to 0 when the fluid is at rest. Now the third term is going to be equal to our gravity term. And what's going to be the differential in pressure with height z? It's going to be equal to minus rho g. We're left with only dp dz out of the three terms that we had. So if we look at our equation above, the gradient just becomes dp dz is equal to minus rho g. And we can go a step further, and if you remember in module 1, we also had the definition that rho g was equal to specific weight. Okay, so that's also equal to specific weight. So we can say, as a conclusion, we can say that dp dz in a fluid at rest is equal to minus the gradient. Now, what if we bring over the dz to the other side? So let's say that dp is equal to minus gamma times dz, and then we can integrate both sides. We can take the integral of both sides to get the difference in a fluid element or in any element height, right? We can do an integral throughout and solve for that integral. So we end up getting that, and we can do this integral from 1 to 2, from position 1 to position 2. We end up getting that pressure 2 minus pressure 1 is equal to minus the integral from 1 to 2 of gamma dz. Now, is gamma a constant within a fluid or not? We don't know, right? We have to see. We're not really sure if gamma is a constant or not. Gamma could be a constant, but remember gamma is made of rho and g. G never changes, but rho could change. Okay, in a liquid, it's highly unlikely that density will change much, but in a gas, density could change. okay? And in a liquid, density could change too at very, very high pressures. So what this equation tells us, first and foremost, is that this equation tells us one thing. It tells us that the pressure difference is related directly to the change in Z. So that means that we can state that pressure is the same at all points on a horizontal plane. And what can we say about pressure if we increase the depth of a fluid? If we increase the depth of a fluid, we actually increase the pressure. So pressure goes up if we increase depth. And we'll do some examples to define that after as well. So this is a good rule to remember. Pressure increases with depth of the fluid. Okay, so now let's look at liquids specifically, and most liquids. So if we have a liquid, we can assume that most liquids are going to be incompressible. Okay, it's an assumption that we can usually make within this class, except at very, very high pressures. And we can say when something is incompressible, that density does not change. And density not changing means that we can, from this equation here, P2 minus P1, we can take out this term and move it outside the brackets because it's going to be constant. Density does not change. And if we do the integral from 1 to 2 of dz, we end up getting a very simple equation. P2 minus P1 is equal to minus gamma, which is now outside of the integral, times z2 minus z1. Okay? And we can rearrange this equation if we want to into defining a pressure head. So we can say that the pressure head, and I'll explain what that is in a second, the pressure head is just pressure measured in height. And pressure measured in height is just rearranging this equation to say Z2 minus Z1 is equal to negative P2 minus P1 over gamma and over gamma. So we have this equation right here. We just rearrange the equation and put the pressure in terms of the height difference now. So now we're looking at Z2 minus Z1, it's giving us a certain pressure. And we can go further than this and just flip the signs. So we can just flip all the signs and do Z1 minus Z2. So instead of Z2 minus Z1, we can say Z1 minus Z2 is equal to P2 over gamma minus P1 over gamma. And pressure head is a very good example of how we measure atmospheric pressure. So atmospheric pressure is not always measured as atmospheric pressure is not always measured as a pressure, as a absolute pressure. Sometimes it's measured compared to a vacuum, and it's measured compared to a vacuum in millimeters. So atmospheric pressure with mercury, for example, is given, instead of giving it as a pressure value, it's given by 716 millimeters of mercury. So it means that a column of mercury would go up 760 millimeters compared to a vacuum. That would be the absolute atmospheric pressure. Okay, that's how we actually measure the pressure outside. We can use millimeters, and then we can convert those millimeters to the actual atmospheric pressure by just plugging in to this equation right here. If we plug into this equation, we have Z1 minus Z2 is 760 millimeter. Pressure 1 would be 0, and pressure 2 would be the one that you're trying to find. And pressure 2 would give you a certain pressure very close to 100 kilopascals with those 760 millimeters of mercury, and the gravity and density on the bottom being divided by it. So pretty interesting. Okay, so we're going to take a break now. We're going to stop for this part of the lecture, part 1 of module 2, and we'll be back in part 2 of module 2 to continue discussing pressure and starting to do some example problems. Okay, so we'll be back in part 2.